Right. Hi, everybody. Good morning, afternoon, or good evening, as usual. I'd like to move on to topic 5 today. And in this video, I'd like to cover, well, I hope I can cover the whole of topic 5.1. Topic 5.1 is called Introduction to Soil Systems. And it's basically just a series of statements of facts about what soil is, how it's formed, what it is, and soil structure and texture. You can see the main things I'm going to cover above my head. First of all, I want to talk about why soils are systems. Then we'll talk about soil structure in terms of the layers that form them. They're called horizons. And the whole thing is called a soil profile. And then I want to go back to talk a little bit about transformation and transfer processes within soils. And then finally, we'll cover soil texture and what makes soil texture. Okay, so there's quite a bit to get through, but it is all, as I said, pretty much statements of facts. I've pasted in the knowledge and understanding sections from the syllabus here, as you can see. So let's just have a look quickly what the IB expects you to know. So first of all, the IB expects you to understand what a soil profile is and the different layers that form a soil. They're called horizons. And then we'll talk about soil systems, soil system storages in terms of organic matter, organisms, nutrients, minerals, air and water. Then we'll talk a little bit about transfer of material within soils. Inputs and outputs. Obviously, that's part of what makes soil a system. What goes in and what goes out of the soil system itself. Then we talk about transformation processes. And then to finish, as you can see there, we'll talk about soil structure and soil texture. So I won't read through all of that. You can pause it there if you want to see that in a bit more detail. But let's move swiftly on. Okay, so first of all, the question of what is a soil? Well, it's quite a hard question to answer actually, because soils are, first of all, atmosphere. They contain gases from the atmosphere. They're part lithosphere. That means they contain minerals, which are derived from rock, or the lithosphere itself. They are ecosystems themselves because they are homes to living things, so therefore they are part biosphere. And because they also take part in the water cycle, soils are also part of the hydrosphere. They're comprised of regolith, which is weathered or broken down rock. They're comprised of organic material. And as I've already said, they're already composed of gases and water. And therefore, that means that soils are solid, liquid, and gas altogether. Because they take so long to form, thousands of years or tens of thousands of years, soils are considered to be a non-renewable resource. They do take a very, very long time to form. Okay, so I said we'd talk about soils as systems first of all. So I've split this slide into the components of a system: inputs, outputs, storages, and processes. I'll just talk about transformation processes in this part. First of all, in terms of inputs, soils have inputs of organic matter and inorganic matter, and also they have inputs of energy. Obviously, it's a statement of fact. In terms of outputs, materials are taken out of soils by plants and animals. They radiate heat and energy, or they reflect sunlight. So energy is also an output. And they also erode, which you can think of as, in addition as an output, maybe a transfer process as well. They store organic material, nutrients, living things, minerals, air and water. And in terms of transformation processes, these things are going on inside the soil: decomposition, weathering or breakdown of minerals, which are the components of rocks, and the recycling of nutrients, including nitrogen and carbon, as we've already seen in those cycles. Just a note there I've put as well, soils are in and of themselves ecosystems. So there are biotic and abiotic factors occurring within the system, within the soil system. I'm not going too fast. All right, then we come to the second section on my list of things to cover above my head, which is soil structure or soil profile. Now, I already said that soils are made up of horizons, and horizons are layers. And you can see some of those layers here. So first of all, the top layer we call the O layer, so kind of this section. It's generally black. It contains a lot of organic material and decomposing material, which we refer to as humus, like leaf litter, decomposing leaf litter. It's generally a very thin layer, not very old, generally black because it's decomposing. Beneath that, we've got the mineral organic layer or horizon, which we call the A horizon, which is this part. It's generally quite difficult to tell the O layer and the A layer apart. They're similar colour, they kind of occur together. So the mixed organic layer or the A layer is the older layer of decomposing organic material. It can contain sometimes an amount of clay, which means it can waterlog, therefore possibly contains a large amount of water. It's the area that farmers plough down into, and it's the area in which plants generally grow. You'll see that the roots extend further beyond the A layer, but it's the area where you get a lot of root systems as well. Okay, beneath the A layer, we have what's called the B layer or the alluvial layer. This is the layer where water can leach down into. So therefore, water can leach materials from the O and A layers down into the B layer. It can have a lot of clay. In some cases, it can be clay rich. It can contain a lot of iron. That partly explains the red coloration. And it can contain humus from the O and A layers. And it's the layer into which water, as it infiltrates through the soil, can carry material from the O and A layers. And then beneath that, we've got two other layers, the C and the R level layers, which we can consider together, which we call the bedrock. The C layer is slightly weathered rock that is the basis of the soils, and the R is the bedrock itself. Living things and plant roots don't really penetrate down into the C layer, and certainly not into the R layer or the rock layer. So it's a fairly simple diagram. It looks like there's very, very clear layers, and sometimes in soils there are clear layers like this, sometimes not. For two reasons. One of the main reasons, as I've put underneath the diagram, is that worms move up and down through the soil, and therefore they kind of blur the edges of these layers. It's not usually that clear cut. And you also have plant roots growing down, which kind of break up the layers. And you also have the movement of materials by leaching of water as it moves down through the soil profile as well. Okay, so the main layers that we consider are, first of all, the very thin O layer or organic layer, the A and B layers in which plants grow, animals live, and plant roots can penetrate, and then the C and R layers, which are the rock layers, which are the parent material for the soil, but into which living things don't really penetrate and plant roots don't penetrate. Okay, so all that made reasonable sense. Here's some photographs. I choose these because you can pretty well see very, very clearly defined layers. So in this one, you can see these. This layer would be the O and the A layer together. Difficult to tell them apart. The O layer will be very thin and the A layer thicker. Beneath that, the B layer. I think I would just make out plant roots growing down into that layer. And beneath that, down here, the C and R rock layers. And similar here. Notice that it's very usual to put something for scale into these as well. Here you've got a little compass and here you've got a shovel. Okay, so that's soil horizon or soil structure. Moving on again. How are soils formed? Well, they're formed, first of all, from the top layer where organic material decays. and they're also formed from the bottom where rock weathers. So soils are formed in a top-down process, but also in a bottom-up process. And they are a mixture of minerals from rock and organic material from the surface that comes from decaying plant and animal material. The main processes involved in that are weathering, translocation, which is the movement of substances. As you can see, they're both downwards, as water flows downwards, usually, and by earthworm movements and that kind of thing as well. Also, the growth of plant roots can mix up the layers, as I said before, as well. In some very dry environments, desert-like environments, water can move upward due to evaporation, which can be a bad thing because evaporation of water and translocation of water upwards can bring salt from the water table, especially if it's close to the coastline, and that can lead to salinization of soil, which can pretty much destroy the soil. I've used the term here, glaying. Glaying is the scientific term for waterlogging, and that occurs when either usually the B layer or the A layer contain quite a lot of clay. Clay, as we'll see in a minute, are very, very small particles which don't allow water to move through. So therefore the water stays close to the surface and leads to waterlogging and possibly flooding. Okay, and then the final sentence I've said there is human activity can have a very big effect on soil formation for a lot of reasons. First of all, we cover soils with concrete and cover them completely. We trample soils either by human activity or by moving animals or by moving heavy machinery. So if you're walking in the wilds, it's very important to stick to footpaths. Try to leave soils alone to form and sustain themselves. I already said that soils can take thousands or tens of thousands of years to form, so it's very important we look after them, and we look after them carefully. Okay, so a few more things. Moving on now to soil structure. Obviously, soil structure is important because the main use of soils are for cultivating plants. I've said that a lesser use is for extraction of peat. Peat in Northern Europe, especially in ancient times, very, very high level of organic material. So if it was dried, it could actually be used as a fuel. So in Northern Europe, very often peat was used for cooking and for heating. To allow cultivation of plants, soil structure needs to be sufficient, first of all, porosity. It needs to have sufficient spaces between particles to allow water to flow through. But it shouldn't be too porous so it allows too much water to flow through so it becomes too dry. Also, it needs to have the ability to retain not only water but minerals and nutrients. The perfect soil is called a loam soil. And a loam soil is a soil that has the best combination of large particles and small particles, as I'll try to show now. Okay, large particles, well, gravel is not usually considered to be part of soils, but they'd be large, kind of rocky, stony pieces of material. Sand, very large particles. If a soil is too sandy, then it will be too porous and it will allow water to run through it too easily. The smallest particles are clay, which will be invisible at the scale you can see on the screen. And in between sand and clay, you've got silt. Small particles, but which have some porosity. If you want to see the scales, you can see it there. The scale is in millimeters. So gravel is of the diameter of approximately 2 millimeters. Sand, a bit less, 1 to 2 millimeters. Silt, I'm not sure what you would call that scale there, and clay, very, very tiny particles. Okay, so as I said before, pore size determines how water can drain, and how much air is also held within the soil. That's just as important as holding water. And the particle size also determines how easily water and nutrients dissolved in that water are retained within the soil. A very light soil, a very dry soil, would be largely sand, very coarse and easily drained, and therefore you can't really cultivate plants in a sandy soil. It doesn't retain enough water and nutrients. A heavy soil would be a soil with a lot of clay, more than 25% clay. That means there's far too many small particles, which means it becomes waterlogged. It holds too much water. So even though the nutrients are present, it doesn't contain the right amount of earth to allow plants to grow in that particular soil. The best soils are somewhere in between. A medium soil, or what a farmer would refer to as a loam soil or a loamy soil. Incidentally, that reminds me of the old statement of what makes a good farmer, or how do you recognise a good farmer? Well, a good farmer is always outstanding in his field. That's a little joke there. Please don't write that down. Okay. All right. I think I've pretty much said this. This is what makes a good soil is the right amount of porosity versus the right amount of surface area, especially to retain nutrients. And I'm going to finish with a chart or a diagram. I'm not sure the correct name of this kind of chart, this graph. I've just heard it referred to as a triangular soil chart. And it basically allows you to define a soil based on its percentage of clay versus its percentage of silt versus its percentage of sand. This is one of those kind of funny looking graphs that the IB likes to throw at you, especially in paper 1. Okay, so what you do is you see these lines across diagonally and horizontally. In terms of clay, the clay soil, the numbers are horizontal, which means you read across the horizontal lines. You'd read across there. The silt line, or the silt numbers, are facing diagonally like this, so you'd follow the numbers down in that direction. And the sand numbers are tilting upwards here, so you'd follow those numbers upwards. So what I can do is I can give you a percentage of each of those three components. You might want to pause the video for 10 seconds and see if you can work out what kind of soil I'm referring to. So if I gave you a soil and we made measurements of that soil and we decided it was 10% sand and 20% clay, and therefore 70% silt. See if you can work out what soil I'm referring to. So I would suggest you pause the video just for a minute or so now. Okay, so if you've done that, let's do it together. So in terms of sand, which is at the bottom, we've got 10%, so we're reading upwards along this line. In terms of clay, we've got 20%, so we're reading across this line. And in terms of silt, we've got 70%, so we're reading down the diagonal from here. Okay, so if I follow those lines upwards with a dotted line, I follow that line down with a dotted line, and I follow this line across, I can see that all of those readings converge at this point, which would mean what I'm referring to is a silty loam soil, which will be a fairly good soil for cultivation, but not perfect. The perfect soils are within this shape here, this loam soil. Okay, so I believe that's the conclusion of everything I wanted to talk about in topic 5.1, Introduction to Soil Systems. As I said, it's just a series of things you really need to learn. There's not an awful lot of extra understanding needed there. I hope it was helpful, and we'll consider this a little bit more in our class. All right, take care everybody, and I will speak to you soon.